For centuries, humanity has looked up at the stars and wondered if we'll ever truly join them. Today, we're standing on the threshold of a transformation that will redefine what it means to be a spacefaring species. The first bottleneck is leaving Earth. Traditional rockets cost thousands of dollars per kilogram to orbit. But imagine a space elevator, a carbon nanotube cable stretching 36,000 kilometers into orbit, turning space access into a climb rather than an explosion. Recent advances in materials science are making this once impossible dream increasingly plausible. Beyond elevators, engineers are designing orbital rings, massive spinning loops encircling the planet, anchored by tethers that create launch points at any location on Earth. These structures could slash launch costs to near zero, turning space infrastructure from a luxury into a utility. But getting to space is only the beginning. The real prize lies beyond Earth. Asteroids contain trillions of dollars worth of platinum, water, and rare metals. Companies like Astroforge are already planning missions to mine near-Earth asteroids, turning space resources into the fuel and building materials for a sprawling solar civilization. To travel deeper, we need new engines. Chemical rockets are too slow for interstellar journeys. Nuclear fusion, the same process that powers the sun, cut a trip to Mars from months to weeks. Private companies like Helicity Space, backed by Lockheed Martin, are racing to build fusion engines that could make the entire solar system accessible within decades. For the ultimate speed, scientists are exploring antimatter propulsion. When matter meets antimatter, the resulting annihilation releases more energy per kilogram than any other known reaction. NASA has already begun researching antimatter-catalyzed engines that could theoretically reach significant fractions of light speed, bringing nearby star systems within reach. Not all journeys will be fast. Project Hyperion, a recent global design competition, has produced stunning concepts for generation ships, massive self-sustaining vessels carrying thousands of people on 250-year voyages to habitable exoplanets. These are not just spacecraft, they are entire civilizations in motion, with ecosystems, cities, and cultures evolving across centuries of flight. For those who don't want to wait centuries, cryogenic hibernation offers an alternative. Scientists studying torpor in lemurs and other hibernating animals are developing techniques to safely slow human metabolism. Imagine sleeping through a multi-year journey to Mars, waking only when your destination comes into view. Once we leave Earth, where do we live? O'Neill cylinders, giant rotating space habitats the size of countries, could house millions with artificial gravity, agriculture, and entire ecosystems. These aren't sci-fi fantasies anymore. They're serious engineering proposals for the next chapter of human settlement. Fast forward a few hundred years and the vision grows even grander. Dyson Sphere's megastructures that envelop entire stars to capture their energy represent the pinnacle of a Type II civilization on the Kardashev scale. While building one may be centuries away, the first steps, solar collector swarms and automated construction, could begin this century. From space elevators to Dyson spheres, the path from a single planet species to an interstellar civilization is no longer pure speculation. It is an engineering roadmap. The technologies we develop in the next 50 years will determine whether humanity remains bound to Earth or becomes a species that spans the stars. Every great leap in human history began with someone asking, "What if the next great leap is ours to build?" The stars are no longer distant lights, they are destinations.